Good morning, everyone. Good evening. Depends for whom. Today is the second webinar for ArcFlash Risk Assessment, where I will try to explain you a bit more about what is ArcFlash study and a bit about me. So my name is Marcin Ruta. I'm a power system consultant. Last 15 years I deal with electrical engineering, and from which the last 10 years I deal specifically with power system studies, including ArcFlash Risk Assessment. I think I did over 150 studies all till now. I don't count it, to be honest. A bit introduction for the webinar for today. So I try to keep it under 30 minutes in total. Then we have a Q&A session, which typically is 15 minutes, but it can be longer. It's no issue with it. And yes, it will be recorded. I would upload it on my YouTube channel and also via newsletter on LinkedIn, so you can find and track the information. If you have questions, try to use Q&A box on. I can actually show you this. You please try. There is a Q&A box here. I don't know if you see it in English or Polish, but try to use this. It will be easier for me to track it down later. So let's go. So we will start. I'll explain what is ArcFlash study, scope of work, and a bit of a reporting. So what is ArcFlash study in practice? I like this. I make this some time ago to explain step by step. So typically, when we talk about the ArcFlash study, you might look on it as a circular event or as a project. So if you look as a project, we always start from the contact. So we have to define scope of work, information for quotation and so on. The next step, then we start is data collection. And data collection means we collect all the documentation, drawings, single line diagrams, information about the electrical systems. And also it means if you are on site, we do a visual inspection for shock hazard, non-compliance, or some non-conformities. Then we go into the system modeling. So all this area, just to show you like this, it's part for the electrical engineer that's actually doing the study, not for the customer. You will be helping, most of them they will be helping, but this is for the electrical engineer, power system engineer. So we create the model in electrical software, most of the time, electrical calculation software, to run all the calculations. And by calculations, I mean that we have to run a short circuit study, selectivity study, and I will explain this in details in a minute. ArcFlash analysis, equipment evaluation, and shock hazard assessment. Normally, when you do this, you will get results, and then we have to review it and provide improvements or recommendation for improvements. Typically, those recommendations are site-specific recommendations. And if we have something optional or as it may be done as an option, then we discuss it with the customer. You have to wrap it up, everything in the form of a report, and provide all the calculations, background, everything else, recommendations, ArcFlash labels, ArcFlash results in easy to read report. Then we step into the ArcFlash training, which means that we have to provide ArcFlash training, but also report presentation, explain how to read the results from the report, maybe help with the PPE selection, things like this. And then we go to the end where it's a final step, we finished. We might go into what-if studies to propose some hardware and software solutions if needed. There is a 5 years review time, which means that if nothing changed in the system after 5 years, we'll review it. If something changed, we review it after the change. And of course, this model is useful for the support for any other electrical activities or design on site. So that's how this looks on project, let's say, level. If you are familiar with risk assessment, you might look on the hierarchy of controls, which is given in an FPA, but also I think if you look on the risk, this is very similar across every risk assessment. So hierarchy of control is that kind of looks like this. It's showing you the effectiveness of some actions from most to least effective. I like to add to this identification, because we start all of this once we know what's the problem, and this is the whole point of ArcFlash risk assessment, main goal. But if you run ArcFlash risk assessment or ArcFlash study, it's important to know that some of the things like this has to be implemented in it. So it's not only identification, but we also have to go through elimination, which is the most effective way. LOTO, for example, lockout tagout, I did asterisk here because it's not exactly eliminating, but it's a big step. Arc quenching device, which is a very nice thing to have. No live work, of course, this is a preference. But if we cannot do this, we go the substitution, so exchanging the hazard with something else. So you might use lower voltage, like low voltage below 50 volts, which is most of the case not possible on existing projects. But we might replace, for example, switchgear with arc resistant or internal arc classified switchgear. That's possible. Awareness. So this is optional to have, but green means that it should be in our alpha study. Awareness. So we should have training for sure. And like today we do webinars, so we create more awareness. And ACFAS labels is a way of communicating and providing information about the hazard. Engineering controls. This is very site specific because it means isolate people from the hazard, put some barriers, remote operations. And it very depends where we are and how it's possible. So what we can do. Administrative controls, electrical safety plan, that's the first thing. Sometimes there are some specific work instructions. And this has to be adapted to what we did. So it has to be in line. And at the end, we have a personal protective equipment, which means that we need to select PPE based on our calculations or table method, depends what we are using actually in this case. So when I talk about identification, I mean that the main goal for ACFAS analysis is to identify the hazard, so incident energy in this case, in calories per square centimeters, in joule per square centimeters, depends what we are following. Define hazard area, so ACFAS boundary. So if you refer to previous webinar, you have more information about it. And recommendations, of course, for improvements and identify required PPE. This is kind of a minimum steps, let's say. So what this means, this is example, very small part of a model in electrical software. In practice, it looks like this. So this part is representing this small line, medium voltage switchgear. There's a lot of parameters behind it. This is a transformer, medium voltage to low voltage, and this is a low voltage switchgear like MCC or main one. So you would like to know what's happening here. So once we do it, you will see the results. And let's assume it's after all the improvements we did. And we know that this is 9.55 calories per square centimeters here. And we have to use this kind of set of PPE. And for the low voltage, it was 30 calories approx. And we have to use this set of 40 calories per square centimeters. And but it also helps in different ways. So if you have all the calculations done, you might match proper mitigation techniques to decide which one is the best. Adjust protection settings to improve actually situation. Make some hardware upgrades where it's needed. Make correct PPE selection, so improve it. And of course, working procedures upgrades, that's what I said before, ACFAS training, labeling, and make some priorities for your modernization plan if needed. The question is, do I need ACFAS study at all? The short answer is yes. It depends really where you are, but I would say, as OSHA says, for example, we need to provide the proper PPE against electrical hazard and have it documented. Documented, I mean risk assessment. And from latest IEEE 1584 test and latest release in 2018, we know that above 208 volts down to 2000 amp short circuit current level, we still can sustain arc in some cases, not all of them, but in most of them we can do it. So everything which is above 208 and 2000 amps of short circuit current, it should be included. And above, let's say 50 volts, that's what technically standard says. Well, this is good from engineering point of view. It's a little bit impractical for end users, because if I ask where you have short circuit current above 2000 amps, barely one person on 100 maybe will know. So instead of this, we follow, which is much easier to find out the size of the protection device. So as a rule of thumb, we follow like everything above 63 amps will be included in study in the scope of work. However, there is always something left, so we include it after site visit. Question is, does anyone in the company operate electrical equipment? And most likely, yes, there is someone. If you have any corporate requirements, If you are from US, Canada, or Australia, probably there is something. And if there are any country guides like NFP 17 US or CSA Z462 in Canada, DGUV recently in Germany, or not recently, but it's in Germany also, or EN 5010 in Europe in general. So in short answer is yes, we need it. And why we need this? So besides common reasons, like where we have to perform sometimes some activities in higher risk areas, and we need to know what kind of possible severity is of possible or potential accident. So we need to identify this backlash severity, which means incident energy. We need to identify the protection problems. We need to identify equipment rating issues and properly address PP selection and address mitigation actions. And that's why we actually do it. It all starts with numbers. The second question or third question is where we have to do it. So there are some technical background behind it, but all the installation have to be assessed individually because there are some differences by electrical engineer. But since all the electrical systems are built in very similar way, we can roughly say that you start from your supply level and you go down to the machine level. Machine level means everything, sometimes like machine line or motor. So in practice it looks like this. We start from medium voltage switch gears, go down, maybe there is generators, UPS system, battery energy storage system, PV or wind, depends what you have. Low voltage switch gears and distribution boards, panel boards on site, above 50 volts of course, and 208. Machine lines, I mean like machine lines where they are quite long. Bus ducts and type of units, and final circuits if needed. This is not really specified well, so this is this 208 and above 2000 amp shows a good current level. But if you have your ARCTA study already in place, but it's outdated or it's not up to date, you have no idea what to do next, you have no idea what PP is needed and when, you don't have any recommendations for improvement. Sometimes there are no recommendations because it's okay, but in practice there is always something. There are further steps that are not clear what to do next. You don't use it, so you have a tick box approach, but there's not much I can do about it with such attitude. It's not implemented in electrical safety plan, or you feel the study is poor quality on output is not according IEEE 1584.1. So I will explain this in a minute. So what I did, I thought it would be nice to do ARCFAS compliance audit, where we actually review ARCFAS reports and results, verify the report content and scope of work that's supposed to be done, check implementation on site, check awareness. So generally, if there was ARCFAS training, if people know what's happening, and verify PP selection. This is kind of very nice, I would say, overview of what's happening on site for already existing. When we talk about the scope of work, then I have to refer to the few documents. So very common you will hear about NFP 17, there's 2021 version, which is very good. This refers to IEEE 1584 as a guide for calculating, and IEEE 1584 refers to IEEE 1584.1 as a scope of work. So there is a much longer name for it, but it defines what you have to deliver and what kind of scope of work for calculation should be. And there are also other standards that you might use. I can recommend Mike Frayn's book, very nice one if you would like to read it. Very nice thing to wrap up and easy to read. And if you go about the standards, and I have to say that I'm more EMEA region oriented, so I put a lot of focus here to show how we approach it in EU. But in EU we have a council directive which generally says what's the responsibility about the safe work and PPE. Then we go to EN 5010, which is the first hazard about the operation of electrical installation standard. And it explains, yes, there is a need for protecting against short circuit and arcing. And on this level, I would say that in US, for example, there is a OSHA 1910-269 Appendix Z, which will probably be somewhere in between those two, like on the same, let's say, level. Of course, you will find in Europe IEC 61482, which is something similar to STM for testing PPE. Those are the standards for testing PPE. They will not tell you how to select it, but how to test it. So again, we go back to NFPA 70, which is our handbook for electrical safety. It is mainly, let's say, used in US, but if you don't have anything, this is a very good point to start. And I really recommend it because we follow this actually in Europe as well. Somehow, I don't know, we have very little such documents like this. CSA Z46221, they are very similar to each other, but there are some differences, depends, of course, in which country you are. And NANES, I wasn't really aware about this, that in Australia they have their own way of selecting PPU and also calculating, which is a little bit different than those two. And DGUV is an information node in Germany about the box method PP selection. You might also hear, if we talk about the higher voltage test and result and calculation, you will see that there is Electrical Power Research Institute technical report that they investigated the longer arcs. This is generally thing which should be in line in OSHA results. And IEEE 1584, this is our main guide. So 95% of projects will be done according to this standard. You might also hear more often about the DC arc flash because we have UPS, battery system, battery energy storage systems. So this is coming more often. It's not exactly well introduced, but I think it will come in the next revision as far as I know. But you will see maximum power method, which is very conservative, and then Stokes, Open-Lander, and Poker method, which are recommended for calculating DC arc flash. And bunch of support standards. I can recommend NFPA 70B if you prefer. So when we go about the scope of work, that was the goal for today. So the scope of work, again, we define by checking electrical drawings. That's the best way. If you don't have it, you have to create it eventually somewhere during this process. We have to just know what's the amount of installation, amount of equipment to assess where we finish. And as a rule of thumb, we go down to 63 amp three-phase protection level as a starting point, which can always be extended. This is important because the scope of work and this is very prone to low quality of execution. So you have to be careful, and the best is to follow IEEE 1584.1 requirements, which is this. This is bigger document, but I summarize it in this way that you might see that, okay, data collection means that we have to go on site, collect the data from the real world. And the good practice is to write a report after it with all the non-conformities that we find from safety point of view. Would be nice. Modeling, so we try to avoid Excel modeling and hand calculations, which are good for one or very small systems. But if you have a big and complex system, this is not very useful. So usually you follow commercial software like ETAB SKM, Easy Power, and more to run electrical studies. And we should include at least short circuit study and multiple scenarios, configuration, min, max, UPS, generator modes, whatever you have. Last data center project, I had 16 scenarios. Based on short circuit study, we run equipment withstand evaluation. So we would like to verify short circuit rating of our equipment, breakers, panels, and so on. Then we also do selectivity analysis. You might also know it as a protective device coordination or discrimination study. That's the same. So we need to do it to review problems with protective settings of protective devices if they are all working well. And this allows also for recommendation part to do. Then we have our main goal, which is arc flash risk assessment. So that's the main thing we will have to do. Sometimes you might hear load flow. It's not really added value for the arc flash itself, but it might reveal loading problem, which means, again, something related with equipment evaluation, which this is the good thing. Of course, recommendations. So usually there is a second part of the calculations for recommended part, like to reduce arc flash energy to improve protection from selectivity point of view, arc flash labels, arc flash training, and report. So all of this has to be documented. Studio output and report. And I'll show you an example what I mean by this. So data collection is, okay, we collect all the information from site, depends what kind of study it is, what kind of location it is. So transformers, switchgears, bus ducts, everything else you will find here. It's important because we need existing data from site, not from documentation, unless it's verified really, but from the site. And there's always a difference between field data and paperwork. And I tell you, I was recently on site, which is still under construction. It has brand new documentation and is already not correct. So it happens. So and site visit also allows you to do visual inspection for any shock hazard violation like and non-conformities. So you can write the report lecture, and it's good to do it with to-do actions. And also site person who is involved, which is, I think, good learning point for them. So example of data collection photos you might get. This is an example of a data collection report, which, for example, I write when I come back from site, where we've been, what kind of panel, what was the problem, how to, what to do, and what's the related risk level. I try to keep things simple so you very easily see where to fix something. The next step is to create digital twin model. And digital twin model means that we have to recreate the electrical system in electrical software, like SKM or ETAP or Easy Power, whatever. And this is the base for next analysis. Now its important part is that not every software can do the same thing. So sometimes it's required by customers. Sometimes it's your own choice, and not every software has the same capabilities. So they don't support certain standards, or they have some limitation for use in future. It's very specific stuff. I follow all of them if I need. Those two are my preferred, and more of them depends what I really do. So you have to be, it has to allow you to create multiple scenarios, compare the results, and provide recommendations later on the data, and also document it very well. So example from the SKM, partly from ETAP. So you create the model, and this is partly also about, it is part of creating single line diagrams also. If you are very detailed, you can use it for doing this. The next step, as I said, is short circuit study. So again, we perform the short circuit study as a base to do anything with arc flash. It's important because we would like to verify equipment short circuit rating. And I'll show you why in a minute. It's like pass or fail. Does it work properly in this situation? It very depends where you are. We follow ANSI or IEC standards. Is it onshore or offshore? Is it AC or DC systems? Important to know is that we cannot be over conservative, because we don't look for the max current, but the worst case from arc flash point of view, which sometimes mean minimum currents. And again, example of how the results might look like in maybe not in report, but in software. And this is an example why it's important. So there's test. I hope you can see it. So this was not good for clamps. And this was okay. And the next video is a little bit different. And this is definitely not good. You will see why the short circuit rating is important. If it's not done correctly, that it might lead to much worse damage. So that's short circuit going into arc flash. The next step is to do a selectivity analysis. Selectivity, as I said, is protective device coordination or discrimination study. Depends how it's called, is the same. So we would like to ensure that our protective device works in the coordinated way, which means that there is enough time interval, depends how it's realized. Sometimes there is a communication between them, like zone selective interlock, but they have to act as fast as possible and limit the fault to the very limited area where the fault is. So in practice, it makes a very big difference, because you don't want your whole site to shut down because of a small fault, or the half of factory goes down because of the small fault on motor. So it has to work properly. And selectivity is has to be done as a compromise between settings of operation fast and arc flash itself. So this is the first reason why this is not done in arc flash studies. And as an example, so I think you can see it, that's not selective situation where you have main low voltage breaker not selected with the feeders, and there is also medium voltage overlapping, and we improve it, slightly improved from Alpha's point of view, but a lot improved from medium voltage and low voltage protection point of view. And usually it's supposed to come with some kind of description why and what happens and how we improve it and what's the recommended action. As an example, I can show you only that was happening in Manhattan. It's a very extreme situation when you had a blackout. I think that was for 5 hours or something. 73,000 people were without power. Cost a lot of money, of course. So, but that's the extreme situation when something is going not okay or works well, but consequences are very big. Our main goal is arc risk assessment. So we'll calculate the arc instant energy for existing and recommended situation. We provide recommendation for improvements, technical recommendations. So settings, sometimes use all the equipment that you have on site, and this will be recommended situation. The difference is that you have to keep in mind that existing situation results is just identification what's happening at site actually, and that's it. It's nothing else, and you can stop there, but there is no recommendation very often that will follow up. And recommendation situation provides you insight to what's possible, how we can improve our system, how we can reduce energy and improve safety. And it takes quite some effort and knowledge to do it. And this is the second thing that's why this step is ignored in ARCFIR studies, at least in my experience. You might show this as a result of ARCFIR. You might show it on the graphically. Depends on software again you are using. So you can show it on as a graphic on software. Very often you will see it in the form of table. I like to add those colors because I use it across my reports, because it's very easy to see now where is problem, at least from my perspective. And that's what I said to you before, when you summarize the results, you have existing and recommended, and technically I like to add the comments, what's happening and why the results are so high, and then the recommendations, so what we recommend that we can get these values, for example, from 19 to 11, what we can do. And when we finish with ARCFAS labels. And ARCFAS labels is a final result of a lot of calculations. So it's not that you ask for labels, you ask for calculation, and labels is just the thing that you put on a panel as a part of awareness in the hierarchy of controls. So we would like to provide the information, clear information to end user, so to electricians that will be working on installation, so they know what is the energy, what kind of distance they have to follow, or what kind of PPE they have to wear. There are multiple ways how those labels looks like. To be honest, I don't know, it's more than 50, probably more than 100 templates. Depends on software again. There are some requirements what might be and might not be on the label. Important to know is that it always have to be in local language. So it's not that it always go in English. It always has to be in local language. If I have a project in Poland, it's in Polish. If it's in France, it's in French, and so on. In Germany, it's in German. So it's, in my feeling, it has to be done this way, because it's done to protect people, to help them to work. What is important here that we have some difference. So you might see the difference here. Those are labels I very often use, and you will see that the shock hazard zone is a little bit different. And then in, let's say, NEC regulation or NFPA, because we have a little bit different values in Europe than, and in some countries they are different. So I keep it separated. I don't follow, let's say, NFPA 70 distances in Europe because it makes no sense from legal point of view. And I will show you an example how substation ARCFAS may look like. Just pay attention how long it takes. And I think transformer is on this side. Not true. And you think it's done, yeah? It's finished. Have a look how far it went. I think it's 6 meters, 7. I think there is even extinguisher down there. It will not be used. So there is no sense to go there with the extinguisher now. It takes quite some time for this thing to stop. Yeah. It's still there. I even found the place because I saw the name of restaurant, so that was in Cambodia. It wasn't written anywhere, but I found. I don't know how to spell this city, but that was this substation. So overall we provide everything that we did in form of report, and all the input data, all the assumptions, all the calculation results like short circuit, arc flash, time current curves, load flow, study results, or power flow. All of this goes into the report, including the comment, summary, labels, everything else. In the recommendation part, because we need to have it documented. And important is all the finding that has to be easy to read, not really buried inside the report text, like 500-page report or 1,000. Like the biggest one I saw, it was 4,000 or 5,000 pages, hard to read. And the recommendation is nice when they are highlighted or clearly remark what the difference they make, impact on the results. And good practice is to keep the report easy to read. And I can show you how I do things. So I'm not showing you the whole report because a lot of things, but in generally there's a report which is limited to what I showed you before, and a lot of attachments, which is technical attachments from calculation. Then you would like to share, or you have to document it and share it, but not necessarily it has to be in form of report. So we approach, and because that was all for today, I might say what's the next steps. So I told you that I plan 10 to 12 webinars for this year. And the next one is an example of the study. So I will actually take the one of the study and go through it and show some findings and what we did and why we did. And the next one is overview of the mitigation solution. So what we can in generally do to improve our safety from hardware, software, and some practical point of view. And there are a few more which are in preparation. So you might, if you will be checking my LinkedIn profile, you'll probably find a newsletter that I created specifically for this, after 2022 webinars. And this is only used for sharing information about the upcoming webinars and follow up. Like from this one, I will upload the information from Q&A and also the recording on YouTube. A link, it will be there. So it's, I think, should be quite easy communication tools. But if you go on LinkedIn to my contact details, you will find my YouTube channel link and everything I will upload there. So now it's time for Q&A session. So let me check. I didn't look really on chat box, but I will go through it. Okay, so let's go. Presentation, the recording will be available later. What is ISC standard for ARC study and what should be minimum voltage requirement to perform ARC test? Okay, ISC standard for ARC study, there is no ISC standard for ARC study. We only can follow ISC 60909 as a short circuit current calculation, but IEEE 1584 is a standard that we also use in Europe because it's international, it's not US related. I don't know what you mean by minimum voltage requirement to perform ARC test. If you mean testing the PPE, it's 2 kV if you do it open arc, and if you do it on box test, it's 450, I think, volts. Mentioned 5 years review requirement rise a question the legislation or jurisdiction applied. Is this 5 years review period a part of legislation? Does it apply US, Europe, rest of the world? To be honest, I don't know. 5 years is a given value in NFPA that is required to review study every 5 years, or there's a maximum time. And the background for it is that 5 years is a time in industry where it's enough time for things to change. And 5 years is not that if you change something in your system, that you don't have to change. So general rule of thumb is if you modify something in your electrical installation, like you change your transformer, change cables, maybe change settings or switch gears, then you have to update your arc study. If nothing happens for 5 years, then after 5 years, you have to review it and check if everything is still correct or up to date, because maybe standard change or something like this. For BS, what type of arc flash study required on safety level? So BS is battery energy storage system. And what kind of study? So on BS, you have AC side, which will be IEEE 1584. And of course, depends on the voltage level. Up to 15 kV, it will be IEEE 1584. And on the BS, you also have a DC side, which means that you have to follow DC arc flash study. Up to you what you choose, because there is no guide physically written, but I recommend Stokes Openlander or Pocket method to be used as a DC arc flash study. And if you use ETAB or SKM, you will have it included in it. Okay, I don't see this here. What is the best solution in case of fire for substation rooms, I think? Automatic extinguishers like FM200 CO2. In case of fire, yes, that's what you wrote. CO2 maybe not, because CO2 is, as far as I know, it's forbidden in some countries because it causes some death of people. You know, it's throw out the air from the substation, so if you are inside, it's dangerous to you. But it will not help you till there is an arc, as the video that I showed you before. You will try to extinguish it, but it will not help you. It's till there is an arc fire, you don't have a chance really to extinguish it. So you have to wait until the power is cut off. That's the problem, for example, on PV plants. Can you suggest the minimum voltage and ampere to consider arc flash hazard? So as I said before, you might start as a rule of thumb from, depends where you are, 208 or 230 volts level, and then 63 amp miniature circuit breaker protection, which is like B, C, D types. So if you start from this, there's usually not much to add, but if you have to, then probably there will be some maybe few locations. And even if you do it, it's very likely that below 63 amp there will be no arc flash risk, or arc flash energy will be below 1.2 calories. Not always, but in most of the cases. As you mentioned, 95% of projects use IEEE 1584. If we did our short circuit coordination study based on IEC, and now we want to do arc study using IEEE by ETAB or EasyPower, etc. Do we have to rerun our short circuit study based on IEE standard, or there is no obligation for IEC? Either IEC or IEC short circuit study could be used as an input for arc study. What is digital tool approach here, SKM, EasyPower, ETAB? So since I work mainly in Europe, I might say that the best is to use IEC 60909 for all the short circuit calculation, because that's the once IEC world standard, and most of the softwares will allow you to do it. So I know the SKM will allow you to do it, and ETAB also will allow you to do it. There is no if you did it with IEEE NC standards, then it's probably good to rerun it, because you will see some differences. So generally, I align a bit all the IEEE calculations to IEC Word. And as far as I know, it's not forbidden, because IEEE tests are not somehow related with, I think the bigger question will be if you have 50 or 60 Hertz. That would be a bit more valid question. But in our practice, it's not no big issue. Follow IEC 60909, because then your protection and your results are more in line with what's happening. If the calculation incident energy exceeds 40 calories per square centimeter in many locations, how would you fix this? As we all know, arc flash is all about time. So usually it's very easy to fix it, but it very depends on your local situation. So if I have something which is above 40 calories, which means that there is usually long time. The long time is coming from something. It might be from protection, it might be from assumptions made from the study, I don't know. But if it comes from protection, you might check if you can improve it. Very often you can improve it. So to drop below 40 calories is very easy. If you cannot drop below 40 calories because you have some medium voltage fuse or something different, then you might look into the mitigation techniques as, for example, arc flash detection relay or arc flash relay. That's also very easy to do. Which is accurate to use in arc flash study, actual fault clearing times or 2 seconds arc time per IEEE 1584. First, actual fault clearing time. So 2-second rule is not about the calculation, it's about escape time. So you might use it if you want. For example, if you say we have plenty of room in our substation, and if something happens, we know that this person has chance to escape. But if you are, like I saw recently, it was confined space, like 80 centimeters, and you have a wall, and if you cannot escape from it, then you don't use 2-second rule. So you always use actual tripping time. Doesn't matter what's happening, but sometimes you might put the limit for calculation on 2 seconds. It's actually good to check first if there is any issue without 2 seconds. If you see 2 seconds in your calculation, you should check what would be the actual tripping time. Some software allows to use comprehensive short circuit method. Do you use this method for arc flash evaluation, or do you stick with IC 60909? Is it good practice for use comprehensive method for arc flash study and IC for recommended evaluation? Do you share software models to the clients? So yes, I share software models to the clients. It depends really if they really want, but most of the time I share it. And I would say if you can stick, if your software allows you to use IEC 60909, stay with IEC 60909. And then you have all the equipment evaluation with the same value, all your protection are aligned with the same value, and all your arc flash results are aligned to the same value. Because if you're comprehensive and you start to play with this, then you will start to see the difference of current, and this difference might be big or small enough for you to see the difference in arc flash results. So I would say, or you stuck with IEC 60909 or you go with comprehensive. But if you are in Europe, you should follow IEC 60909. Can you suggest the minimum voltage ampere to consider arc flash hazard? So I think it was already there. Is it required DC for arc hazard? For DC, yes, there is a limit. So below 50 volts or 48 volts, there was a discussion if there is, if the arc can sustain, and technically arc can sustain, but usually the results are low, even if they are quite long. So if you look on the PV plants, you see that, you know, you can create the arc, but it doesn't look like it's very energetic. So it's very easy to create it, but it doesn't really put a lot of danger. But you need to know on the voltage level, because if your system goes up to 700 volt DC and 40, 50, 30 kilo amps of short circuit current, that's a lot. And I did recently few studies, and they all been above 1.2 calories for batteries. Do you need to do arc flash study for gas insulated switchgears? There are no exposed conductors. That's a good question. Technically, no. Because your gas insulated switchgear will be also internal arc classifying, most likely, because it will be medium voltage. So you can calculate it if you want, but if you don't have an exposed conductors where you can initiate the arc, it's hard to say, okay, why we do it. Eventually there will be a cable connection where you can calculate it. How much do we need to carry out arc flash studies on temporary equipment, for example, low voltage rental generators and distribution? If you will be working on live on this equipment, would be nice to have. And you can do it on the generator itself, because now the generator will be supplied, yeah? So if you calculate it for your generator, on the outgoing on generator, probably this will be enough. Otherwise, you have to recalculate the whole site, assuming that you have a generator connected, which sometimes is done when we already have information what kind of generator might be connected. But I would say this would be much easier if you calculate it for your generator itself. So you have your generator calculated, because it will not change. And the rest of the system, it's now point of question if it should be recalculated or not. You might say, okay, we don't do anything now because it's temporarily supplied with the generator. So we avoid this 1-2 days maintenance. It's a good question. Here's my key. So, as I have understood, in US, the AFRA study prevention mitigation falls to kind of two different fields of legislation. One is OSHA or NFPA rules for work safety. The other part is the AFRA study itself, and that falls to IEEE 1584. Is this correct interpretation? Yeah, I would say yes, but IEEE 1584 is a guide to make calculations. So it's just one of the method. And in NFPA, you have few methods actually that you can use. So IEEE is just the most popular one because it's the most well documented with the best test and empirical one. So yeah, that's correct. And what about the Europe? It's a long question. Is 8939EC the only regulation given? Now we have EN 5010, which is electrical safety operation of electrical installation, which provides you information about the arc flash. And then we go next. That comes in very generic level about work safety. Is there anything more concrete or detailed what comes to the regulation? It's clear that there is no European counterpart for IEEE 1584, but do Europe have clear regulation for arc flash incident and arc flash energy levels? As you can see, I'm trying to find some regulatory basis for the arc flash protection practice. So technically there is nothing. In Germany, they made an approach with DGUV, but this is for the box method test and it's theoretical one. So they didn't share any test yet or to prove it. Some countries just adopt NFPA and IEEE 1584 as a guide to assess arc flash, and I would say it's quite good approach because it's complete. So if you follow NFPA and IEEE 1584, IEEE 1584 for calculations for most of the systems, and NFPA 70E, let's say you pick specific parts on NFPA 70E related with electrical safety, then you are on the good side. From legislation point of view, I can tell you that there is EN 5010, which is a European norm standard which provides you information about the arc flash that you need to protect. That's what I showed before. And it refers to NFPA 70E in this document, so you might use it. In generally, all the standards are not obligatory, to be honest. So even in US, the NFPA 70E is not obligatory on arc flash, or maybe in other way, arc flash study is not obligatory, but you have to document that you did arc flash risk assessment. So it depends if you would like to take responsibility on this. Okay, it goes, if the calculated incident energy exceeds 40 kelvin per square, okay, this was already done. Juha, IEEE calls for the voltage short circuit current. Having said that, does define the voltage current, or does IEEE refer to some other standards? In my opinion, it's not clearly said in IEEE 1584. They don't have like very nice way say standard. It's called NCC 37, but there's a group of standards in US which defines how you calculate short circuit currents. You might refer to former Violet book from color books from IEEE. And let me check if there was. Okay, so did you mention the program FabDoc for calculation? Is it because you have no experience, or this is, or do not think is appropriate? As far as I know, FabDoc doesn't do any arc flash calculation, as far as I know. But on the other hand, my experience with, let's say, low voltage calculation softwares, but there's a big group of the softwares, it's not really handling well arc flash, and generally calculation if you have bigger systems. I think this I answered. IEEE was updated last 2018. Were there significant changes in the incident energy calculation results versus previous edition calculation? With the facility with multiple buildings challenging in updating in the last standard and 5 years assessment. Where is it? 5 years assessment. Okay, so there are differences because now you can more precisely specify your electrode configurations. So if you follow VCB or HCB before, probably you will not see big difference. But if you start now to see some VCBB breaker, so vertical conductor breaker barrier, so now you might see change. But generally they also adjust the more coefficients inside the calculations. So I would say you see the difference. Probably you see down, most likely, but it's hard to say, generally just to update it at some point. Was there anything else, or we are on? I think we have it. Is there anything else? Oh, okay. How best to model modular UPS battery strings with system rated 5000 amps with multiple battery strings to reduce the fault level and ultimately reduce the energy? So that's an interesting topic because I had the same one recently. And okay, we have 5 minutes left. So I have the same. So if you model UPS and your batteries are connected to the common DC bus bar, so you have multiple panels connected to DC bus bar, it very depends what kind of protection you have in the battery panels, or if there is protection at all. So you might expect that on the main bus bar it will be worse. But in practice, the worst situation is on the panel itself, on the battery panel. So the simple answer is, if you can run separate connections to each UPS module, this will be better from Mark's point of view. But in practice, you might improve it a bit with the protection settings on the DC side. Okay, I think we are running out of time. It took a bit more than I expected. So I would like to thank you all for coming today. If there will be any questions, please write it to me and I will try to put it on a newsletter paper. And thank you very much for being with me today, and see you next time.